Before we go on and do the further investigation of activity 2, which is where we're going to do the samples where we take 10,000 samples of different sizes, starting with n equals 4, I want to talk about something called the standard error, which we have mentioned before. The population standard deviation is sigma. Now, we know that when we have a population, that it might span, let's say, from here to here. And so the standard deviation will be a measure of that dispersion. When we start taking samples, even small ones, the n equals 4 that we've seen before, we know that it isn't going to have the same standard deviation. It may well be that it has the same range, but it's inevitable that more of the data is going to go towards the middle. When I say the data, I mean the sample means are going to go towards the middle. Because to be at this outside edge, as we've seen, if we just think about the 1 to 10, which we had before, with a uniform distribution, we know that that's equally spaced along here. It's uniform. But to be at this end, you'd have to get 1, 1, 1, 1. To be at this end, you have to be getting 10, 10, 10, 10. There's a lot more ways of getting the values towards the middle. There are many, many ways of getting the 5.5 mean there. So the standard deviation is going to reduce because there's going to be a greater density of the results in the middle. Now, I've already mentioned this before, but the amount that it reduces is by the square root of n. Divide by the square root of n. So when we're talking about n equals 4, the distribution of the sample means should have sigma over 2 as its standard deviation. This is called the standard error. And we're going to see that as we work through the investigation. Okay, so I'm set up here with my code here for samples of size 4, which we may be able to find in here. Sample size is 4 and number of samples is 10,000. So we should get a pretty good picture depending on how the bins have been chosen for the histograms. So let's have a look at this one. And what you should be able to see on this histogram is that it has a slight positive skew. Now, we would expect that. Remember, we're dealing with a binomial 20 0.05. It's very skewed and the mean is 1. The theoretical mean is 1. The taking samples of size 4 will smooth out the skewness of the original distribution, but not completely. And that's why we still see a positive skew with n equals 4, which is why we need larger samples to make it more and more normal. And hopefully we'll see that as we go through. Notice over here, theoretical normal, we've got those values. The standard error, theoretical, is just the previous value divided by 2. And look how close this one is. The standard deviation of the sample means is very, very close. I bet we won't be able to produce that again that close. So let's try that. Let's do another sample, even with 10,000. Yeah, and you can see it's not as close this time, 0.4809, but everything else I said still applies. We can see the positive skew, and the red curve here is the theoretical normal curve. So it's not a terrible fit. So moving on, I've now got the code for samples of size 9, and let's run that and see what that looks like. That big value there is probably due to the way that the bins were chosen. If we'd chosen them slightly differently, we might have a higher bar here and a higher bar here, maybe a higher bar here, and this one would be a bit lower, so it might fit a bit better. The histogram is a bit sensitive to how you choose the bins. Let's have a look at stuff to do with means. The sample mean to 2 decimal places is the same as the theoretical, and it's 0.3209. The standard deviation of our sample means is not that far from the standard error, which, remember, is 0.9749 divided by 3. That's the square root of 9. So that's what that one looks like. Let's just do another one. Even with 10,000, we're going to get some sampling difference. I can't see a whole lot of difference, and this is slightly annoying that this big bar here in the middle, but I think it would take a lot of fiddling with the bins to make it look better than that. So I moved on now to sample size 25, and let's have a look at what that looks like. We've got a couple of bars that are a bit high. Again, choosing slightly different bins might work because we can see these bins here are a bit lower, but you can see this tendency to move towards the middle. We're still at sample size 25 for a very skewed distribution, so we're not going to expect to see a perfect normal anyway. Let's look at the standard error, which in this case is the standard deviation divided by 5, and the sample mean standard deviation is really quite close to that. So this sigma over root n is looking quite good. Let's just try a second one of those, see what it looks like. And we can see it's not really all that different. It definitely has a slightly different shape to what we had before. And 0.1952, that's closer in this case. And the mean was the same at 1. We're going to have a look at 225 now. So here we are, sample size 225. Let's generate one of these. And so we can see the histogram's not too bad. There's a few bars above and below. I've added, because I didn't like the thing about the bars sticking above, for this one, with it being a larger sample, it was worth doing this KDE calculation, the smooth data. The KDE is sort of a better histogram that's more continuous and less in bins. It's beyond the scope of a Year 12 course, and indeed I didn't even cover it in either of my degrees in mathematics, but it was something I could find out about and add to this. And you can see the blue dotted curve actually fits the red one really quite well. Let's generate a second one of those and let's see if it's much different. And yeah, it doesn't follow it quite as well, does it? But also it's not lumpy, the blue. And you can see the histogram does fit reasonably well. And if you fiddled with the bins, you could probably get it looking even better. The standard error should be the standard deviation divided by the square root of 225, which is 15. And you can see the standard deviation here really is quite close for those sample means, although the mean of those is 0.99. I've only got that though to 2 decimal places, so it might actually be 0.994 something. We don't know, but even so, it's quite close to the mean. So you can see how this works. Taking 10,000 samples just gives us less variation in the samples we get. If we only take 25 samples, we might well end up with a disproportionate number of things that are down here or up here. But when we take 10,000, they're more likely to be to the middle. But the sample size of each sample is the important thing. The sampling distribution is what we're looking at. And we can see once we get up to 225, even for this very skewed original distribution, we end up with something that really is quite normal by the time we get to that sort of sample size.